and this lesson will be covering the tower design process that we go through for the competition. And just before we get started, I'm just gonna mention a couple things. First of all, if you're not talking, we'd ask that you keep your mic muted just to minimize any background noise. And also, if you have any questions during the presentation, feel free to type them in the chat, which you can find at the bottom of the screen. And we'll try to either get to them during the presentation or after we're finished if we have to. So with that, let's get started. Okay, so just a quick introduction. My name's Alex, and I'm going into my PY after completing 3 years of civil engineering at U of T. And this will be my 3rd year on the U of T Seismic design team, and I'll be a senior design and analysis lead this year. And now Maher can introduce himself.
Yeah, so my name is Maher Absar. I just finished my 3rd year of civil engineering at the University of Toronto as well. This is my 2nd year on the U of T Seismic design team. And yeah, I'm looking forward to the next competition. I'm going to pass it back to Alex so he can talk about the topics for today's presentation.
So for today's presentation, we're going to be going through 3 main topics. First of all, we're going to cover the general design process that we go through for our towers. And after that, we're going to go into a little bit more depth on how we can use SAP 2000 as a tool to do some of these aspects of the process. And then we'll finish off by talking about some of the things we do after tower construction, such as testing and calibration of the tower. So before we're able to design our tower, we have to know what objectives we're trying to meet with our tower that we build. So the first thing we want to do is maximize our final annual building income, which is a score that's given for the competition. And it's a function of a number of parameters, with the main ones that we're interested in being the peak roof acceleration, peak roof displacement, and tower weight. And the acceleration and displacement values are measured for the first ground motion, which we call GM1. And this is the low intensity ground motion, whereas GM2 is the more high intensity ground motion for the competition. So the second objective that we're trying to accomplish is to prevent our tower from collapsing. So for this, we want to ensure that our tower can survive the second ground motion, GM2, since this is the more intense ground motion. So in general, if we're able to survive GM2, we could probably assume that we would survive GM1 as well. And a second thing that we're looking into for tower collapse is torsion. So just to give a bit of context, torsion is a twisting motion that is usually caused when there is asymmetry in the tower in the direction that it's being shaped in. So if we want to avoid torsion, we generally want to make sure that our tower design is symmetrical, but that's not always possible. And the reason I've listed this under preventing tower collapse is because having too much torsion can increase the forces that the members in our tower experience and increase the likelihood that we will have a tower collapse. The third objective that we want to meet with our tower is for it to be easily constructible. And this is because any tower that we design, in the end, we have to actually build that tower out of balsa wood. So we want to make sure that we can actually do this. And naturally, it has to be easy to construct. So after we know what we're trying to accomplish, we have to start designing. And the first step in the designing process is brainstorming. So brainstorming is the part of the design process that is more involves a lot of creativity. And generally, we'll be given a different set of rules for each year's competition. And with those rules, we have to then generate a number of different design concepts that we could potentially use for our final tower. And once we have a whole set of design concepts, we then have to narrow it down to one most efficient concept. And that we can determine based on the objectives that I talked about in the previous slide. So whichever concept is able to best meet that whole number of objectives that I just talked about is the most effective tower design. So just kind of give an example from last year, we were given this restriction of the L-shaped floor plan from floors 1 to 5. And from that, we came up with a number of ideas and ended up settling on this design, which transitions from an L shape into a pentagonal shape on the top floors. And one thing to note is that there are both some qualitative and quantitative analysis that we do when determining which tower concept to use. So for example, something such as being easy to construct is a more qualitative analysis that we just do by looking at the different designs, but we also go ahead and model all of these designs on software such as SAP 2000 to determine its structural performance in terms of different things like displacements and accelerations, since that you can't as easily tell just by looking. So once we settle on a final concept, such as the image on the right here, as you can see, this is just kind of like an empty shell of a tower. So we need to go ahead and optimize this. So the optimization process is where we take this shell and turn it into something like this image on the right here, where we have columns, beams, and different braces on it. And even in this image here, there's even a shear wall at the bottom. So we have to come up with what to use for all of these different parameters. And the one concept that I want to bring to your attention, which was covered by Daniel yesterday in his lecture on the seismic basics, is the response spectrum. So this is a very important concept for optimization, and it allows us to see what the expected accelerations, or you can even look at displacements, are for a given period. And since we're trying to minimize both accelerations and displacements, by looking at a response spectrum graph for the ground motions of the competition, we can determine which ranges have the most minimum values. And these are the ranges of period that we want to target with our tower design. So for instance, if we built a model on SAP 2000 and it told us that the period of the tower was 0.16 seconds, if we look at this response spectrum graph, we can see that the acceleration, the maximum acceleration of the tower is expected to be around 5 Gs. But if we were to increase that period somewhere to either around 0.18 seconds or maybe down to something like 0.14 seconds, we could have a much lower acceleration of around 4 Gs or even lower. So naturally, we would want to adjust the period of our tower to fall into one of these more optimal ranges. So since we want to do this, you might be wondering, how do we change the period of the tower? So there's kind of the general idea is if we want to increase the tower period, then that means we want to reduce the stiffness of the tower, and vice versa. If we want to reduce the tower period, we want to increase the stiffness of the tower. And doing this, we can change a number of parameters, and the two that I want to highlight are the bracing schemes and the column sections. So for instance, on the left here, I have two different possible bracing schemes, double X and single X. And if we were looking to have a more stiff tower, we could try using this double X bracing scheme, whereas if we wanted to reduce stiffness, we could try this single X scheme. And there are naturally like many other combinations of bracing schemes that can be used. These are just two examples, but this just gives you an idea of how you can use different bracing schemes to adjust the stiffness of your tower and in turn to change your tower period. The second parameter that I want to talk about is column sections. So again, if we wanted to have a more stiff column section, we could try using this quad column, which is on the right. Whereas if we wanted to maybe reduce the stiffness, we could change it to something like a triple column. And again, there are other columns. You could have a single column, double column, or all sorts of different combinations of balsa wood pieces. But these are just two examples of different ways that you can adjust the stiffness of your tower using columns. And these aren't the only parameters that impact stiffness. There are other things you can add, such as shear walls, which I mentioned previously. And overall, the idea is to change these parameters to adjust the tower period and keep iterating until you reach a period that falls within one of those optimal ranges that's dictated by the response spectrum. And this will sometimes require many different iterations, since it's hard to know how much the period will change by making a single change. And also there are different ways of accomplishing this, like how I talked about, there's bracing schemes and column sections. So you could sometimes accomplish the same period through different methods. And this leads to another concept, which I mentioned at the beginning of the objectives, which is reducing tower weight. So another thing to think about is which method can result in the optimal tower period while using the least amount of column weight. So once you're able to create a completed tower that's been optimized for the period ranges that you've targeted, then you're ready to start constructing, and that kind of brings an end to the design process. So now Mahar will go into a little bit more depth into the ways that we can use SAP to accomplish some aspects of this process.
Now that Alex has talked about some of the numerical values we focus on when designing a balsa wood tower for the competition, we need a tool that gives us these numbers for our many ideas so that we know which towers give us the best results. SAP 2000 is what the team at UFT has been using for a couple of years now. This is a structural analysis software that can be very useful in industry as well. For today's tutorial, we will go through the general applications of this software for our team and present what it looks like visually when navigating through the software. So for more information, you can refer to the link on this page when the slides are posted. This basically takes you to a YouTube playlist created by Computers and Structure, the creators of SAP 2000. And for the junior design and analysis members present, I believe we'll hold a meeting where we'll go through the tutorial documents prepared by previous UFT Seismic members to give us a more detailed understanding of modeling in SAP 2000. So to get started, when starting a model in SAP for a tower, you need to define material properties and also draw in the geometry of the tower. So SAP 2000 allows you to define your own grid dimensions, and then you can draw using the multiple views that are available. And also you can put in your restrictions such as supports at the base of the tower to finish your model. You also need to input the ground motions. These are provided to us by the competition hosts. And also you need to define some load patterns. For example, the dead load, which is representative of the gravity or self-weight of the tower itself. And then you can define load cases in SAP 2000 or combinations as well. So when we actually test the tower in real life under the ground motions, obviously gravity is acting on the tower at the same time. So that's represented in the load case of the dead plus GM1. And the same thing applies for the second ground motion. So once we have our model set up, we can obtain the numbers that Alex were talking about in terms of accelerations and displacements and the period after SAP performs its calculations and whatnot. So here is what the software looks like visually. This is one of our models from last year. As a member of the team, you may have a model like this with the materials and the geometry defined, and then you may want to change the bracing schemes or member thicknesses. Alex mentioned to achieve change in period, for example, and then try out your own ideas and then see the results. So to see the results, you can press the play button, see outlined in red, and that will take you. That will allow SAP to perform its calculations. Another thing to note in the bottom right is you can change the units to whatever convention you're comfortable with. So once you press that play button, you're presented with this window. So when modeling in the dead load in SAP, we define it to include the competition loads. So this includes the metal rods and the plates you may have seen in the pictures of the previous competition towers, as well as we can put in the ground motion 1 and ground motion 2. And our last load case that we will run is the self-weight load case. And this is a load case that does not include the metal rod and plates and just the tower itself. And this is useful because this allows us to obtain the weight of the tower on its own. And again, that's something we want to minimize in terms of the FABI and the material cost of the proposed structure. So once you have your cases selected, you can press Run Now, and then SAP will perform its calculations. And in this case, you can view the results by going into Display and Show Tables. I selected 1 point at the top of the tower so that I don't get a huge table with accelerations and displacements for every single node in the model. So here I selected 4 tables that we mainly care about. You can also go back into the model, select all the members, and then select element forces frames, as you can see right here. And this will allow you to find minimum and maximum member forces. But for now, we can just select these 4 tables. And then also, if you want to filter your tables to just specific load cases, for example, just ground motion 1 and the dead load, you can just go here and filter that on your own. And after that, you can press OK, and SAP will produce these tables for you. So if you want to switch between tables, you can go to the drop-down list right here and switch between the various tables you've selected. So the first table here is the base reaction table, and this tells us some of the forces the tower is experiencing. We set up the model so that the ground motions are acting in the X direction. And as you can see here, our lateral forces are more significant in the X direction for the ground motion 1 and ground motion 2 load cases. And you can see the min and max values in the various directions. This table is also useful for the self-weight load case. So here we can look at the Z direction, and we have a tower weight of 1.53 pounds. Again, this is in pounds because I selected that as the unit conversion at the bottom right. And I changed that for each table to better suit the numbers we are looking at. So in the context of earthquake engineering and this model building, we'll look at absolute accelerations. So here again, we note the X direction, U1 accelerations. And this is, as Alex mentioned, this is something we want to minimize. Yeah. So for the displacements as well as the accelerations, as I mentioned, these values in the table are for the single point at the top of the tower. Again, we want to note the X direction displacements. And here you can notice that the Y direction displacements are significant too. And this can be attributed to the torsional effects, especially for last year's tower because of the unique shape of the building. Lastly, this is the table that helps us figure out the period of the tower. And we can see the different modes here. This is something Daniel discussed in yesterday's tutorial. But in this case, the period, the dominant period, is 0.199 seconds for mode 1. And we can look at this value and then look at the process Alex mentioned and tweak our tower to change it to a better period. So once we have a tower design for after our iterations in SAP, we need to actually construct it. So last year what we did is we used a Revit model to ensure precision and ensure that it actually matches the analytical model made in SAP. And then you can see the tower is being constructed in the picture on the right. Future Seismic Academy tutorials will go through more detail of this process. In fact, the next one on May 23rd will focus on that, as well as the FABI calculations. So that's the thing we've been talking about that we want to optimize. So this would be a very useful tutorial for our competition. And as well, in late June, there's a Revit tutorial. And this is a very useful software in the civil and structural field. So once we have our tower built, we need to test it. So in the video on the right, you can see the shake table at UFT. This is our test tower being subjected to ground motion 2. For our test tower, we do both ground motion 1 and ground motion 2 testing, and then we observe the behavior to identify weak points to iterate on the next design for our final tower. But for both the test tower and the final tower, we perform some other tests to identify some characteristics. So the white noise test is a low amplitude varying frequency ground motion, which we can use measurements of the roof accelerations by accelerometer to then use a mathematical procedure called the Fourier transform to obtain our tower period. And then we can use the free vibration test, which is a ground motion that suddenly stops. And then this helps us obtain our damping ratio using another mathematical procedure, the logarithmic decrement method. So for the white noise, the graph on the left shows us our roof accelerations that were measured. And then we can perform the Fourier transform, and here are the results. I believe the exact mathematical procedure will be covered in future tutorial, but the general idea is that this helps us identify the fundamental frequency, and then which gives us the tower period, which is 1 over the frequency. And now to match the SAP 2000 model with what's happening in these real-life tests, what our team decided to do is change the Young's modulus to set an effective stiffness of the tower material because there's some uncertainty regarding that. And we assume that that's the parameter we need to change to match the periods. So how that looks like in SAP 2000 is we can just go to the Define tab and then press Materials. And that will bring us to this window. And then we see balsa is already here. You can easily add any new materials using the first two options. So in this case, we'll just modify the material for balsa. And here we can change the Young's modulus from 1 GPa. You can note the units right here. So this is in GPa. And then, for example, we can change it to 1.6 GPa, press OK, and then rerun the model, and then go back to the table I mentioned where it states the period of the tower to see if it matches the period of real life. And we can iterate until it does. So from the free vibration tests, we can get the damping ratio. This process was covered in much more detail by Daniel's tutorial. So I encourage you to look at the recording if you were unable to attend. But this is another number we use to fine-tune our computer model. So what this looks like in SAP 2000 is we can go to, again, the Define tab, and then go to Load Cases. And then this will allow us to change for each of the ground motions. So we press Modify again, and the box at the very bottom of the window will allow us to change our damping ratio. So once we fine-tuned our models, we use this to make our predictions for the actual competition. You may know that the predictions have their own rankings, and in general, this helps us perform well at the competition. So that brings us to the end of the design process journey, and until the next competition, I guess. That also brings us to the end of this presentation. We'd like to thank you for listening, and any questions can go in the chat box.
Daniel had a question earlier. He says, can you explain the difference between nodes and elements in a SAT model?
Okay, so a node is sort of like the place where two different, I'll start with elements. So an element would be the different members on our model. So you can think of all our beams, columns, and bracing as elements, and these all have a certain material property for each element. And then the nodes are the locations where different elements connect with each other. So for example, a connection point where a beam meets a column would be considered a node. So if you're kind of unclear about that during the presentation, that's kind of the difference between the two.